Hey guys, in our previous discussion, we began considering the role of quantum mechanics in materials research. Of course, we intend to rather just touch the tip of the iceberg. We are not going to dig deeper into the different roles quantum mechanics plays in the theoretical research of materials. We just want to understand or acquaint ourselves with at least one prominent role of the quantum mechanical calculations in materials research. As a starting point, we considered a representation of a material, and that representation is rather shown here. So this is an atomic representation of a crystalline material wherein the atoms are regularly arranged. Now, when you consider the feature of this representation, there are two key features. One is how the atoms are arranged, which we refer to as the configuration. The other is the interatomic distance. When we considered the interatomic distance in our previous lecture, we saw that it is possible for us to start from the interaction between the subatomic particles, which are of course in the quantum mechanics level, or the quantum mechanics calculation. So the interaction between the subatomic particles is essentially associated with or can be considered as quantum mechanical calculations. So we can start from these calculations, and it is possible for us to ascertain the lattice parameter or the interatomic distance. So more accurate these calculations are, the more accurately we are able to calculate this quantum mechanical effect, the more accurately we will be able to rather arrive at the interatomic distance. Now what we want to do in this lecture is we want to rather move into the other key feature of our regular arrangement of the atoms or our representation of the atoms here. So two key features. One key feature is interatomic distance, and we were able to arrive at it from the quantum mechanical calculations by considering pairs of atoms. And what we want to now do is we want to look into the other feature of the crystalline arrangement, that is the configuration or how the atoms are being placed, which is rather reflected as the crystal structure. We want to see if it is possible for us to arrive at that feature from the quantum mechanical calculation. So that is rather the intent of this session now. Now, when we want to understand the configurations of the atoms, of course, we have to look beyond the pairwise interaction. So let us understand or consider this configuration here. Now, when we want to arrive at, from the theoretical standpoint, when we want to arrive at this particular configuration and say that this is rather the stable configuration of the material that I am considering, there are essentially two ways for us to proceed. One is I can consider a force field and then allow my materials or atoms to rather to move around and then settle down at a position wherein they are comfortable, experience no force, and meaning there is no further driving force for the atoms to move. So I can start off with a force field, allow my bunch of atoms to move around and settle down. They essentially, depending on how I have estimated my force field, what force field I am considering, they settle down in their location wherein there is no longer any force experienced by the atoms. So they settle down in a position which we refer to as the stable configuration, and ultimately we end up with a configuration that will be the equilibrium configuration. So that is one way to proceed. The other way to proceed is I can consider different configurations of my given number of atoms, calculate the energy associated with each of these configurations, and then say this is rather the lowest energy configuration, so I can expect my atoms of my material to arrange themselves in this way. So there are two approaches. I want to come up with or theoretically show that this is going to be the stable configurations of my atoms in a given material. There are two ways for me to proceed. One is I can create a force field, allow my atoms to move, settle down when the net force settle down at a position wherein the net force is zero. That is one way to approach. The second approach is I consider different configurations, calculate the energies of the different configurations, and then say, depending on which one is the lowest energy, I can say this is going to be the stable configuration. Now, if you consider the approach one, there are two different aspects of physics that are involved. The first aspect is the classical mechanics, wherein I talk about the movement of atoms in response to the force that is experiencing. So I expose my atoms to a force field, they are allowed to move and they are allowed to settle down. The point they are settling down or the position where they are settling down is nothing but the net zero force position. So they move around, they settle down. This all can be described using the formulation that stems from classical mechanics. However, there is also a role played by the quantum mechanics because the force field that surrounds this set of atoms is essentially a quantum mechanical calculations. So the approach 1 involves combination of classical mechanics and quantum mechanics. The quantum mechanics gives us the force field in which my atoms are allowed to move, and my classical mechanics gives me the position wherein my atoms are getting settled down. So R1, 2, 3, let them be the position and the force field. So this force field comes from the quantum mechanics. The position, the stable positions of the atoms, they come from quantum classical mechanics. So I can use classical mechanics to allow the movement of my atoms and finally settle down. I can use quantum mechanics to calculate the force field. In the case 2, in the approach 2, I'm already fixing the positions of the atoms. So all that I'm considering or calculating is the energy that is associated with each of these configurations. So meaning I'm considering the different interactions that I have considered for the pairwise atoms, but in this case for different configurations, and then I'm calculating the corresponding energy for these configurations of atoms. So essentially what it means is the role of the classical mechanics is kind of marginal in this approach, but rather the role of quantum mechanical calculation is extensive. It is predominantly what we do in the approach 2. So when you fix the positions of the atoms and when you are calculating their corresponding energy of these configurations, essentially you are relying on quantum mechanical calculations to give out this energy. So that these are the fundamental difference between the two approaches that will allow us to reach the stable configuration. And DFT pertains, in principle, it pertains to the second approach, wherein you start off with the different configurations, you calculate the corresponding energy, and then you say that this is going to be the stable configuration of my atoms. So the way quantum mechanics is related to that of the density functional theory is that the density functional theory, through its foundation on quantum mechanics, helps us ascertain what is the energy of a given configuration of atoms. And when we are able to compare the energies across different configurations, we will be able to say this is the stable configuration. The way DFT allows us to do this is ascertaining something called as, that has to do with primarily the electrons. The way DFT operates is, the way DFT is able to ascertain the energy is primarily to do with the interaction and between the subatomic particles, primarily the electrons. We want to consider the electrons, the way it interacts, and that is a critical reason for it. So essentially, when we want to consider the different configurations of the atoms, we rather focus on the interaction of the subatomic particles primarily or the electrons, and that is a reason for it. We will get to it in a minute. And based on that, we will be able to say what is the stable energy configuration, and that is rather the one-liner that is associated with the DFT. If you take this understanding and apply it to the macroscopic view or microscopic perspective of our material's behavior, we will be able to relate this trinity to that of what we find from the DFT calculations. So what you see here is, rather this is the materials trinity what you have here. So what you see here is the structure of the material that you observe depends on its configuration or that composition and ultimately affects its property. So if you want to arrive at a specific structure, you can arrive at a specific structure through certain composition, or of course one aspect that is missing here is processing. So a given structure can be arrived at through specific composition or certain processing techniques, and when you arrive at the structure, your property is getting influenced. Or the other way to look into this is the properties are essentially influenced by the structure through the composition and processing. And another way of looking at it is, if I want to arrive at a specific structure, I have to alter the composition and processing. So there are different ways of looking at it. So that's why we refer to it as the trinity of materials, meaning all this composition, processing, structure and properties, they are correlated, they are interrelated with one another. You tweak one, you tweak the other. You understand or study one, you are able to understand and study and relate it to others. So when I'm able to study the structure of the materials or the arrangement of my atoms in a given material, the crystal structure of the materials, essentially I may be able to relate it to how it will change with the composition and how ultimately its property is going to change. Now the foundation of it, how my structure is going to change with my composition and how my structure is going to change with my properties, the foundation of it is exploited by the DFT calculations. The way it is exploited, like I just mentioned before, is by focusing largely on the interaction between the particles that are subatomic in nature, and primarily that of electrons. So when I have different configurations, what they essentially have is different electronic structures. So these different electronic structures are going to give me different properties. So when I have different arrangement or different configurations of atoms, I'm going to have different electronic structures, and this electronic structures is going to ultimately influence my properties. The same goes for when I'm changing the composition of my material. When I fix my configuration but replace my atoms, the composition is changing. The corresponding my electronic structure is also going to change. When my electronic structure is changing, essentially my structure is going to change, and also my property is going to change. To say the least, when I say the structure, at least my lattice parameter is going to change when I change my composition, and correspondingly my property is going to change. So what undergirds this trinity, this interrelation between composition, processing, structure and property, is the electronic structure. And this undergirding factor, this is physically what we observe, this undergirding factor is what is exploited by DFT during its involvement in materials research. So what DFT does is it rather finds out, or it rather operates on determining this electronic structure, thereby identifying the suitable crystal structure. So that is essentially how the DFT is formulated to operate. Again, it is important to note that this electronic structure is significantly different from that of the electronic configuration. So when we talk about electron configuration, we are restricting ourselves to a single atom. We want to understand how these electrons are arranged within a single atom. But when we talk about electronic structure, we are considering a bunch of atoms that exhibit a regular arrangement. So we have a set of atoms that form a continuum, and that continuum of a material, the distribution of electrons in that continuum of a material and their corresponding energies is what we refer to as the electronic structure. And this electronic structure, it determines, or rather it dictates, the resulting crystal structure or the configuration of the material, ultimately influencing the properties. So what essentially DFT does is, the DFT, by focusing on or by estimating this electronic structure, allows us to estimate the energy of a given configuration, thereby enabling us to say which is going to be the stable configuration for my given atoms. Electronic configuration is just within the atoms how the electrons are arranged. Electronic structure, it talks about the energy distribution principally of the electrons across a continuum of a material that is made up of different atoms. When the configuration of the atom changes, the electronic structure changes and the corresponding energy changes. So when I change the different configuration of the atoms and find the energy, I'm finding the energy through the electronic structure. And when I'm able to locate, this is my lowest energy configuration. I can have FCC, BCC, HCP. So let's say, for an example, I can consider my aluminum atoms and I can arrange them in simple cubic crystal structure, find the corresponding electronic structure and find the corresponding energy of my configuration. I can do the same. So I can take my aluminum, find its electronic structure when it is arranged as a simple cubic crystal structure, and find the corresponding energy. I can take aluminum, arrange it in BCC, body centered cubic, find the corresponding electronic structure, find the associated energy, then I'll be able to calculate what is the energy of that configuration. Do the same for FCC and do the same for HCP. And ultimately, when I find that one of these have the lowest energy configuration, then I'll be able to say this is going to be the crystal arrangement of my material. So this understanding, so this is essentially what DFT does, and it does it through ascertaining or estimating the electronic structure. So that is the reason when we say that the quantum mechanical calculations of the DFT relies upon the electrons, or predominantly relies upon the electrons, it is this. And the reason why it relies upon the electrons is because when we say that this is our configuration of the atoms, what we are essentially fixing is the position of the nuclei. So the nuclei are no longer moving. The nuclei are now stationary. When I say I'm going to calculate the energy of my crystal, when my atoms are arranged as simple cubic, what I'm fixing is, I'm fixing the position of the nuclei. So the nuclei are no longer moving. So only dynamic component of my system is the electrons. So my energy is now going to change depending on the distribution of my electrons. So essentially my energy is going to depend on my electronic structure like in the physical world. So DFT calculation relies on this aspect of the physical world. So the more accurately I'm able to calculate the energy associated with the electrons or the electronic structure, the more accurately I'll be able to calculate the energy of my system, be it simple cubic, BCC, FCC or HCP. So this way of separating the energy of my continuum, the energy of my crystalline system, we are separating it into the energy contribution from the stationary nuclei and the energy contribution from the mobile electrons or dynamic electrons. So this is something referred to as the Born-Oppenheimer approximation. Of course, Oppenheimer, by now you should be familiar with him, not because you came across him in any textbooks, but at least in a movie. So this Born-Oppenheimer approximation is rather how we calculate or ascertain the energy of a configuration, and what we essentially do is we say that the overall energy can be split into the energy that stems from the stationary nuclei and the energy that stems from the dynamic electrons. And now we are able to, from this separation, we are able to extensively focus on this dynamic electrons, calculate the corresponding energy, and ultimately able to calculate the energy of my configuration, thereby allowing me to say which is going to be my stable configuration. So this is rather the foundation of the density functional theory. So we rely ourselves on finding the electronic structure, and from that we are going to calculate the energy, and based on that we are going to calculate which of these configuration is going to give me the least energy. So with this outline, we will get into the story of density functional theory in the subsequent section. Goodbye.